wait 1 or 2 more minutes. Okay, let's get started. Yeah. All right. Welcome to PIM 122. Not too many people here, but I think we should get started. How many? Do you have a lot of people remote? A few.
Yeah.
Okay. Yeah. All right. So hope you all have seen a note well, or maybe you haven't seen it yet this week. Uh, it should be the same as last meeting. We well, yeah, you should all read this and make sure you follow it. Here's the agenda. So it's a pretty packed agenda this time. So we should, I guess, hurry up. Any comments on the agenda? So I think we have like 10 minutes spare at the end here, but I expect that some of these might take a little longer than the scheduled time. Okay, I'll quickly go through the working group status. So let's see. Since last time we have the BIS drafts, the IGMP version 3 and MLD version 2 and the 3228 BIS, they are in the RFC editors queue, but they are just about to get published shortly, and a couple of these are like in auth48 state right now. Then we have the last BIS draft, 1112. Torles will present that shortly. We didn't really have enough responses during the working group last call, but Brian gave some good comments, and Torles has done a lot more work, so thanks for that, and probably want to do another last call shortly. DR improvements are not discussed this time, and BDR neither. Let's see. Okay, I'll use this one. Okay, point-to-point point-to-multipoint drafts. We have requested publication, so waiting for our AD and ISG. PIM Lite was just published, so that's great, and thanks to Sandy for being the shepherd for that. We got the joint prune extensions for Lisp. They're in the RFC editors queue. We also requested publication for the MOFR draft. So that's in ISG processing. Then we have a couple more drafts that are not presented this time. It's a couple of young models. Lessons learned will be discussed this time. And finally, let's see, we got some AutoConf drafts that they will be discussing. And let's see, yeah, and we got the multipath IGMP MLD proxy, and finally we got this PFM forwarding enhancements that will not be discussed this time. So that's the working group status. Any comments before we start on the first presentation? No. Torles, you're up then. So you should be able to use this thing.
Yeah, it just I'll tell you when it's ready. I gotta click on slide.
Okay. Yeah. Okay. Right. So last version before this one, IETF 120, went into working group last call. Last call window closed shortly before 121 as far as the timeline. Everybody was happy, except for Brian, who provided some very short questions. And I went to the microphone and said, well, let's quickly be done, famous last words. And then it turned out to actually, rambling into one thing that took a lot longer. So the easy things, right? So the meaning of IP is now RFC 8200 compliance. Before, obviously, it meant IPv4, because when it was written, there was nothing else. And now it means like 8200, any version of IP. That, of course, is also explained. So there was a lot of changing of IP into IPv4. And then, of course, also several fix-ups where, you know, the wonderful people of the IETF chose to have new naming for IPv6, like hop limits instead of TTL and other stuff I could rant about, but won't. So the introduction explains now also the content of the document better. And one of the things I woke up to is that I really need to expand the title to say host extension for IP Multicast. And because in before it was just called host extensions, but now it is, of course, not the complete host extension. It's only the host extension and the ASM service interface on top of it, but it doesn't describe the SSM service interface on top of it. And I needed to take these two things apart and describe both of them in the introduction so that people understand there are two service interfaces, ASM and SSM, and they share the same host stack, right? Because there is no different Ethernet binding for SSM, for example, and so on. So that was also simple. It's just the introduction text is now new. And then, of course, also the wonderful new versions of IGMP-v3 and MLD-v2 are now referenced as opposed to the old and buggy ones that we're still having until, you know, these two new ones come out. Well, and that's when the trouble started. So there's this wonderful small text block that was rambling of Mr. Deering. It's in parentheses, so why not simply remove it? And then, of course, Brian stumbled across it, and I was looking through it and figuring out what the heck to do with it. Well, primarily, you know, it has a couple of outcomes. So this is the rest of the presentation talking about this, right? So the special treatment for 224001, that actually is in that text, but it actually belonged into the IGMP version 1 text, which was already removed, right? So that part that we wanted to remove. And the same text with respect to the special treatment is also in IGMP v2 and v3. And in MLD v1 and v2 for v6, of course, we decided to change that behavior. But so removing that part was fine. There is a new subsection of the whole section 10. Section 10 is why the heck, you know, are there changes and you know, what do they give us? But as far as the normative specification, that part is just removed. Now, interestingly enough, the IGMP v3 Lite RFC, probably in oversight, does not have this, you know, must always join to the group, which is also fine, right? So it's really a decision of the IGMP or MLD protocol. So that was simple. Now, the other part, the beginning part, you know, all host groups are recognized as a special case, never forwarded beyond a single network. That is actually a router requirement, right? So that whatever TTL you send, you're not forwarding it. It's a link local scope address. Now, I didn't introduce the word scope, but I did look, can I reference an RFC that normatively state what link local is for IPv4? And there isn't, right? The only stuff where that later happens is in, you know, IANA registry RFCs, which of course later became obsolete and are now just IANA registries. So because there was no normative text for it in another normative RFC, I added text to say, well, link local, and there's another name for it, local network control block. This is link local addresses. There is now a new kind of single paragraph section router requirements, right, which just talks about the link local. I didn't introduce the word scope because the scope stuff came later. And I pointed to the RFCs that introduced the overall scoping for IPv4. So that was basically the leftovers of that small red part. And of course, there is must also be a section in a subsection, section 10, explaining that. So there is also the even more interesting thing that the IGMP protocols specify not to send IGMP memberships for 224001, which wouldn't be compliant with RFC 1112. So I wanted to see what can I do for RFC 1112 bis so that that behavior is compliant, or should it be compliant? So actually turns out that I remembered the history of this whole holy crap, which was that the use of 22400X addresses was started to be used in router protocols like OSPF and others, even before multicast and IGMP implementations were being done. And you don't need to have IGMP to do link local scope multicast, right? You can perfectly send and receive these packets with just the Ethernet filter without any IGMP protocol, because the IGMP is only good for a router to get traffic in from another network, and because it's linked local, you don't need it. So the only reason why we chose to mandate MLD to do that also for link local IPv6 was because we also wanted to support MLD snooping switches. But we had already defined in the RFC for snooping informational that we shouldn't expect any IGMP in link local with IPv4, yada, yada, yada. So this ended up being then the text that says you may not send IGMP for link local IPv4 addresses. So there is a may now that permits it, making all the other RFCs, in compliance with that. But still, if you do like to send it for whatever reason, nobody prohibits you to do that. And then this whole history of the implementations, that is now a whole appendix in number 3, appendix A3. That's the longest thing because it's really convoluted for people to understand, because when I joined Cisco, I didn't understand why the heck are you not sending IGMP, right, in your OSPF implementation. See, this OSPF RFC, even the first one, talks about that you should send IGMP. And why? And because we say so. Yeah, so technically why? Well, no good reason, right? So that's the history that I put in there so people understand all the technical background. But the total changes in the main normative text are really quite minor.
Can I ask questions
Mhm.
now, or?
Sure.
So the first question is about 224.001.
Mhm.
So you say that it can be left to the IGP protocol, right? But are there other RFCs possibly that are using or relying on hosts responding to the 4001?
Yeah, so what Steve Deering said, that other protocols may use it, I think, I'm trying to remember if I found another RFC to use it, and I'm drawing a blank right now.
Okay, because I mean, at least in theory,
Mhm.
if hosts in the future end
Mhm.
up implementing something other than IGMP, or decide
Right.
that they don't really need IGMP, they may still have to listen to that address if it's used for other purposes.
Yes, I mean, we still have enough, 22400X addresses left over, right? So I think we would make a good look whether we give out a new address for a link local new
Yeah.
use for IPv4, or whether we use the all hosts, all
Right.
multicast hosts, actually it
Yeah,
is,
at
right?
least my point is, if it might be used for other purposes than just IGMP protocol,
Mhm.
then it might be best to leave it as part of the multicast host requirements and not have it only in the IGMP protocol, right?
No, I think this is orthogonal. I think whether or not you need to send IGMP memberships for any of the 224.0.0.0x addresses, that is really the decision. The only reason why you need it is because you might want to have an IGMP snooping switch that otherwise doesn't forward the packet to you. And we already have the IGMP snooping RFC saying, no, you must not expect IGMP membership reports in
Yeah.
224.0.0x.
Well, at least one example is people sometimes ping that multicast address just to check which multicast hosts they have
Yep.
on the LAN.
Yep.
So there could be
Yeah.
reasons like that to
And
still have
that
it.
works fine, right? So because we already excluded for IPv4 IGMP snooping to expect IGMP memberships.
Yeah.
So at this point in time, there is really no good reason why anybody would ever want to send IGMP memberships, other than they didn't understand the history, and when they read RFC 1112, other groups in 224.0.0.0x, would you would expect that you should send it.
Yeah. Okay. Just one more brief comment.
Mhm.
You said it's fine that the IGP Lite doesn't mention that it should join this group, but
Mhm.
it's important, right? Because it needs to get queries.
No. It's that you always join it. So I think Steve Deering, I did try to figure out how the heck he implemented that, but the only text that was no, you need to join it if you build IGMP at user level, otherwise you don't get the packets through the Ethernet filter, right?
Yeah.
So there is no risk that you don't join it through the Ethernet filter, right? Because otherwise you wouldn't receive the packets.
Sure.
But
no, so
you
it's,
don't need to send out the IGMP memberships.
Sure, that's true. Yeah,
Right.
sure.
Also a related question. David Lamparter. I do know that switches do behave like this for the /24, but you're listing 224/8 here. Do we know that?
Oh, did I make a typo in
Yeah,
there?
I
Is
think
there an
that's a
/8?
typo,
It should be
Okay.
/24. Yeah, of course. Yeah, sorry. Hopefully it's not in the draft, right? So, but you have a wonderful tablet to check the draft. So thank you. 5 minutes. Okay. Right. Right. So the explanation section. So is I'm a service model. Right. So the initial summary now is explaining better ASM SSM as the service model with a common host stack. And then these new explanation subblocks, right? 10.7, that's the link local. In the IANA registry, it's called the local network control block. 10.8, that's a special treatment of 224.0.0.1. And then 10.9 is the IGMP MLD messages for link local IPv4 host group addresses. So, and the sales pitch, of course, that we need to be aware of is that one of the big challenges when we hopefully at some point in time get rid of this in our working group and get it over to the IETF, ISG, is that we of course want to have the full standard back that 11.12 has. And these things actually, yes, they do add more explanatory text, but the actual requirements and explanation now make this align better with the reality of hundreds of millions of deployed devices than 11.12 was, right? Because it didn't have that may to say, well, you don't have to send IGMP memberships in that space, for example, and a couple of other details, right? So, but I haven't tried to, summarize kind of a sales pitch, but I've tried that all the changes that were done do make it better in that respect or not worse. And we're closing standards gap, right? We were closing the gap that there was no standard specification for defining the link local. That was kind of hidden in parentheses in text that, and now it says must, right? You must not forward 224.0.0x packets, whatever TTL they have, right? So, and that obviously is also something that everybody does. Right, so I think that was it. Questions?
Yes, so about the RFC 791.
Oh yeah, the update. Oh, did I forget the slide about
you
that?
maybe
Yeah,
forgot
yeah, I
that.
forgot the slide to add a slide about that. Yeah, so good, thank you. Right, so I was, and I have a section in the text now that justifies this. The whole point is we had an open issue. It was a to-do whether or not to call this RFC an update to IPv4 791. And I finally decided if I just have it as a to-do, when it goes to ISG, nobody cares, right? So we need to make the claim, of course, it's an update to 791. And then if a majority of ISG doesn't like it, then, well, we drop it, right? So my argument why it is an update is because by implication, you look through 791 and there's nothing that tells you that some address range, let's call it these, 224/8 range would not be subject to the forwarding and processing rules of IPv4, right? So if unicast, if anybody would apply IPv4 unicast processing to these, possible, madness could evolve with someone that actually is doing multicast. So from that perspective, because we're taking the address range away, and completely changing the forwarding rules on it, it's an update to 791. So that's the argument. And I'm not adamant of getting it through. If it is, fine. There is another complex IETF bureaucracy to it, insofar as that there is this standard 5, and that's actually a package of all the things which are not updates. They didn't have the term update when 791 was written, but they have a standard 5 that says this is all of the good IP stuff. RFC 11.12 is part of that as well. So obviously there is also the ask to make the BIS part of standard 5 again and replace 11.12 in it. And there's of course standard 86, which is for IPv6, where of course they did everything different. So standard 86 does not include any of the extensions of IPv6. Go out, figure it out yourself. So I also then said, well, we're not bothering about standard 86. So these standard things in preparation of what comes ahead with IESG are also now in this version. So this is a lot of process. This is a, what is it, 35-year-old document. So definitely, there is nothing wrong in taking our time and doing all these improvements. And I was so happy that Brian triggered me to revisit that part and then, fall into the trap of identifying all these gaps that were missed around.
Yeah, thanks for all that work, and we'll check with our AD and ISG in general, maybe how to do some of this. Yeah, thanks.
I was just thinking that I'm not sure what the ramifications of changing a draft name is when it's already a working group draft, but it seems like this would probably be better to be named PIM Multicast Protocols, or less maybe.
Yeah, it
Multicast
doesn't really
protocol.
matter once it gets published. Well, if it gets published, no one will care what the original draft name is.
So when it gets published, you can just change the name to whatever you want.
You mean the draft name, right?
Yeah, the draft name.
Yeah, no one will see that, right? It will just be RFC some number.
Yeah, that's true. Because this is focused on protocols. And so many of you are familiar with this draft. We have a history of protocols that we're just giving an overview of. It came up in a couple years ago that it'd be helpful to have this kind of a draft. And so we've been slowly developing it. It's going to be a draft that we'll be working on probably for some time. The one that we just added from the last IETF was on reliable multicast. There are a couple additions that we're going to add to this based upon what we have in the draft today. But a lot of us don't have whole lot of the history of reliable multicast. We weren't really involved in the RMT. I know some of you were, but and Bill, but I wasn't. And so their purpose was to standardize reliable multicast transport. And so I just included a little bit about that in this last update, talking a little bit about NORM and ALC protocol, and just talked about, what their purpose was and how the PIM working group later produced our own experimental extension to PIM, which is PORT, for reliable transmission of PIM join PRU messages. And what we don't have in here is maybe a good history of why the RMT working group closed maybe, and why we're at where we are and what we may need to develop in the future. But this is what we did add in since the last IETF. And we're going to continue to make changes to it. Hopefully it's a helpful document to the industry, and thanks to you to provide these suggestions on what we can include. Does anybody have anything that comes to mind right now that we can add for the next update?
I'll try to read through that reliable multicast section and see if I want to add something to that, because that obviously was a very interesting process thing, right? So the problem was really when the working group was created, every researcher on the planet came with 3 proposals. So it became pretty clear that no, the working group could not create good, comprehensive, reliable multicast protocol. Instead, they said, we're just going to define building blocks. And in parallel, there was the thing that actually, the 5 big players, TIPCO, Cisco, Microsoft, and I forgot one, in the industry had implemented a very good protocol. And the IETF said, go away, you're just one out of 500 research papers that we don't want to adopt. And so they had this convoluted process of outside of the IETF defining something called RFC 3250, I think is the number, PGM, pretty good multicast, which was implemented, Windows XP, TIPCO, everywhere, different routers, of course. And then ultimately the IETF gave in and gave it actually, experimental or so, right? And they ran outside of the IETF an IETF process with meetings, everything, because, the PGM, the RMT working group didn't want to have them. So it was pretty crazy. The protocols that you're mentioning, Norm, or so, they were done at the tail end as kind of the most simple reference protocol you can think of from the building blocks we've defined. Right. So yeah, I'll look if some of that might be useful for posterity, because it was pretty crazy.
Sure. Thanks.
David Lamparter, I've got two clarifications questions. First, it currently says that the path in the source tree is determined by the unicast routing table and also known as the RPF path. I do know that we've been asked to support different underlying topologies for this specifically, and we've gone to a lot of work to make that work correctly. I'm not sure if this is intended to be an observation that this feature isn't used much, or if it's just an oversight and needs to be mentioned.
I think it came straight from the documents.
Okay. Then I'll, yeah.
Which one are you specifically talking about?
This is 3.3, where it says it's determined by the unicast routing table. So it's by default might be the unicast routing table, but most routing stacks, as far as I know, support using a different topology. And I do know that we go to a lot of work to support different mixing modes as well, which might be a bit extreme, but we have been asked for this by customers. So it's out there at least somewhere.
Okay.
Yeah, I think that's just maybe just being a little too brief, kind of, or, you know, it's not what many people do, but it's not like what you have to do. Or,
yeah. Another thing is that in 3.5, the RPF is a security feature. I am not sure.
Oh, I see.
I would consider that it's a necessary functional feature, which is a higher requirement than a security feature. Like if you remove a security feature, it still works. In this case, if you remove it, it just breaks. So that's a little bit confusing to me.
Good point.
And last thing, there's this. There's already the section on data-driven state creation. There's also this behavior based on bandwidth or packet rate, where you switch between the RPF and the SPF, and I don't see that mentioned.
I'll double check. I'm not sure. It should be there, but thank you.
I'll pour this into mail as well.
Okay, thank you. We'll include all that. Thank you, and Charles's comments as well. And we need to move on. So thank you. Okay. You there, Nate?
Hey, can you hear me okay?
Very loud. Yeah, just speak a little quieter, which is usually not the case. I'm going to give you slide control. It's kind of a neat input. It's pretty cool now. See if it works.
Okay. I'll talk softer. Hopefully that helps. Okay, so we have 3 documents here, all kind of related. And this is kind of our final review before we do working group last call. So I'm going to try to roll through as quick as I can. All right, so the documents are divided into 3. The first one is a problem statement and requirements. It's got the criteria for evaluating the proposed solution. The second one is updates to the IPv6 multicast group ID allocation. And the third one is an algorithm for dynamically assigning IPv6 multicast addresses. And this problem was first presented at IETF 114. So jumping into the first one, the problem statement. So this is an overview of the networks that we work with on marine networks. You have basically, we're using multicast snooping to prevent high bandwidth multicast data from overwhelming the links to low bandwidth sensors. So when we start looking at how the multicast addresses play out on the network, just a summary of what multicast addresses have. IPv6 multicast addresses, you have 120-bit group ID, and then 2426 talks about the first 2 octets are 33, and the last 4 octets of the Ethernet address are the last 4 octets of the IPv6 multicast address. And when you look at RFC 3307, it says group IDs less than or equal to 30 bits long will generate a unique link local layer addresses within a given multicast scope. So the problem with this is that different nodes, different IPv6 link local addresses, they can generate the same group ID and accordingly the same MAC address. The second problem that you can run into is that the switch address table can have collisions, and this is talked about more in the document. But basically, if you have an address table, oftentimes that is implemented as a hash table with buckets. If you've got 4 buckets in there and all of those buckets are filled, you can no longer add addresses that use those same buckets, and so you need to have a way of basically saying, yeah, the multicast address you're trying to use here is not going to fit into your hash table, and you need to pick a different one. So we looked at different solutions out there. The switch, paying attention to the IPv6 address. Those switch vendors don't support that. Source-specific multicast, not supported by the switch hardware. Madcap, which is it's a way to dynamically allocate addresses that relies on a central server, and within our networks, we don't want any central points of failure. And then ZMAP was an attempt to do a kind of a distributed mechanism for allocating addresses, and that was never published. So we decided to come up with something different. So the solution is a decentralized zero configuration protocol for dynamically assigning multicast addresses. Going into the requirements here, you listen to the document, but we want any solution not to have a single point of failure. It does not depend on user configuration, coexists with other assignment protocols on the network, such as Madcap, supporting operation on a single subnet, does not require internet, multiple applications on the same host, and then detects and resolves the address collisions. Desired features, which are not necessarily requirements, but would be things that we want. They support operation across multiple subnets, does not require significant changes to existing standards, common functionality, uses capabilities commonly provided to unprivileged applications, avoids depending on configuration data, and minimizes network traffic. All right, so that ends the first one, the problem statement. Then we jump into the updates to the dynamic IPv6 multicast group IDs. So just a refresher on the multicast address guidelines in 3307. The group ID is kind of divided up into different ranges. 0, 1 to 3 FFF, that is permanent addresses. Those are allocated by IATA. Then you've got 40 through 7 FFF. Those are permanent, also allocated by IATA. And then you have 80 through FFFF. Those are dynamic addresses. And then those are kind of described in 2 different mechanisms where you'd have a server allocation and a host allocation. One problem we can see immediately with this is that both of those allocation methods, the group IDs overlap with each other, which could potentially be a problem if you're running multiple allocation methods on the same network. The other problem is that the group IDs are conflicting with the solicited node multicast addresses that are currently being used. So basically, if you're looking at the range FF00 through FFFF, you're seeing that there's a potential collision there with 3 different allocation mechanisms. The first one being solicited node, and then the others are Madcap and a host-based allocation. Again, solicited node is required by any device that's running multicast, or IPv6 rather. So our proposal that we want to do here is to set up a range of allocations in the table that is administered by IATA. The first change would be it would update Madcap essentially to say that the range 80 through 8 FFF, that's designated for Madcap assignment, and that doesn't actually require an update to the Madcap, just to the assigned range, and then leave 900 through FEFFF, that would be unassigned, and then FF00 through FFFF, that covers the already assigned solicited node multicast addresses. The idea being also that in short order, we would assign two of the ranges here. The first one, 90 through 9FFF, that would be for the zero configuration algorithm that we are going to discuss next. And then A0 through AFFF, that would be for the GAP protocol. That is, I don't think it's in last call yet, but would be very, very shortly. And then, of course, the solicited one is there, and then there's a large block of unassigned addresses that could be used for future protocols. Okay. And then the third one, this goes into the IPv6 based zero configuration assignment. And so this basically uses MDNS to publish records and to some degree resolve conflicts in there. So you have a record name, which is you are generating a random group ID in that range that we discussed previously. You use that to generate a link scoped IPv6 multicast address and convert that to the MAC address. And then you publish a new PTR record with a corresponding MAC address. So if you can look at the example down there, you've got your group ID is the first line, the IPv6 link local link scope address is the second line, third line would be your corresponding MAC address, and the fourth line would be the name of the record that's published. And this, of course, is kind of in line with what you would see with a reverse address IPv6 and IPv4 record. The contents of the record would be in the name of the application combined with the host name. So in the document, we talked about application.example.local. If the host name would be called example.local. This allows multiple applications to run on the same host. And then you also have a record called veto, and that basically indicates that there's a problem with assigning the address, such as an address table collision. We engaged the DNSSD working group because they have expertise in MDNS and to get comments from them. So we just there were a couple of changes that came out of our discussion with ESCO on that. Basically pointed out the comparison with DNSSD. They're saying DNSSD uses different DNS record types to facilitate service discovery, whereas what we're doing here is we're using a single record type, the PTR record, to facilitate address assignment, and noting that it may be used in combination with DNSSD or by itself, and that we're doing this with the expectation that existing MDNS implementations can be used. We also clarified that address records may be published for the host name included in the record, or they may not be if you're not doing DNSSD. And then we also received approval to only require IPv6 MDNS over IPv6. The idea being that if we're doing IPv6 address assignment, IPv4, requiring IPv4 didn't seem necessary. So the intent again is to move forward with last call on this, and just want to open it up for comments and questions.
Yeah, Stig here. So if I got this right, you have one problem statement draft, and then there is one draft that is basically changing how IANA, that range that is used for group assignment, right? To split that into multiple ranges. And then you got two solution drafts, right?
Right. The one I'm discussing one here for IPv6, and then Dino and Mike have one called GAP.
It's the other one, yeah. So, so one thing I think we need to, I assume that you believe there's a need for both of those solutions, right? Both the v6 one and the GAP one.
Yeah, I think they can both satisfy different, different customers, or both of them are. Either one's going to be better at something than the other one.
Right. So I think may need to have some text in those solution drafts, kind of explaining a bit, what their purpose is, or why this one solution is better for a certain, use case or something like that. It's kind of hard for customers to, or not customers, but implementers or vendors maybe to know which one they should implement. Right.
Sure.
Can we do the calls on the list or with this one at Davis, since they both requested or not?
Yeah, we can. Well, I feel like I don't know. In a way, that the very first draft is really the problem statement draft, right? And see if everyone is happy with the problem statement and if it covers what you want to solve. And in that case, we can do working group last call on a problem statement. But for the solutions, I think we kind of need to first narrow down a problem statement and see that the solutions actually fit within a problem statement.
I think
So
one of the things
uh,
included in the zero conf, I don't remember if it's included in GAP either, but an evaluation of how well the solution fits with the criteria and the problem statement.
all right. So yeah. So one thing also, yeah, it's great if you can, you and Dino can also have another look at the other problem statement and see if you if it covers well what you actually have solved, kind of. Yeah. So I would say the problem statement draft can maybe go soon, and the group ID draft, that doesn't really depend on the solutions, right? So that can also kind of go before the solution drafts, right?
I agree, and I think the biggest advantage to that is it points out the conflict with the solicited node addresses. So it's an existing conflict with server-based allocation and solicited node.
Okay, let's start with the problem statement maybe and check. Should we do a poll or like?
Based on time, we should just probably take it to the list.
Yeah. Okay. Okay. Yeah, I think we have to take it to the list, but we'll check on the list what people think about the problem statement and see if that's something we can start with at least.
You got 8 minutes, Nate.
Okay. So in the last IETF meeting, we presented on some potential issues with with multicast snooping. And so since then, we have started working with some folks from Juniper to actually write a document to address the issue. So the document, just kind of a status update on that. We are going to list it as an update to RFC 4541, which is the multicast snooping informational RFC. We're including both clarifications to RFC 4541 and then also optimizations not considered to that originally. And then also we're going to do an update to RFC 3810 MLDB2. There'll be more updates on that. The document currently contains a lot of to-dos. And jump into what the progress that we have made on there. So just as a refresher from RFC 121, there was kind of a gap in the forwarding rules that are listed there, where it talks about what you should do with multicast routers and what you should do with hosts, but it does not talk about other multicast snooping switches on the network there. So we do discuss that in the new draft document. And then also that there's this issue with non-optimal distribution of the multicast data. So if you're looking at the red stream from switch 1 to switch 2, that stream doesn't actually need to go up to the querier, but it has to due to the requirement that the packets must be forwarded on all router ports. There's also an issue in that the membership reports are only forwarded up to the querier and not down to other switches on the network, and that would prevent the membership reports from the host getting back to the other host. So ultimately, in order to solve these issues, you need to have a better use of reports or the better use of queries. And we looked at it, and the reports would require additional protocols to address compatibility issues between IGMP v2, v3, and MLD v1 and v2. So what we're doing is electing to go with query messages. The problem with that, the immediate question is, are IGMP v3 and v2 queries compatible with each other? And you'd have to look at the checksum for that and how the checksum is defined. The checksum is basically, or the RFC defines the checksum as needing to take place of the whole IGMP message. So if you have an IGMP v2 host getting a v3 query, and it goes to calculate the checksum, it would look and calculate over the whole length, not just the length that it understands. Similar thing with the MLD v1 and v2. Again, it would calculate that checksum over the length of the entire ICMP v6 message. So our conclusion there is that the newer version queries are going to be compatible with older version hosts, most likely if the hosts are implemented correctly. If they're not implemented correctly, the solution would be to update the hosts to do that correctly. We also, there's an issue with the proxy queries that are described in 4541. It basically describes a query with the source address of all zeros. That is not used for query election, but it doesn't address the same problem with IPv6. There's 3 documents listed there that all prohibit using the all zeros IPv6 source address. So while we could potentially update those documents to allow for that, it would also go against existing implementations. And so rather than kind of fight the established precedent, we come up with a new mechanism here. The idea is that we would take one of the reserved bits in the query message and reallocate it as a P bit. If P is 0, which is what it currently would be used or sent out with, that indicates that it is used in query election. And if it is 1, then to not use it in query election. We also noted that the IGMP v3, the corresponding bit in IGMP v3 is left unmodified. We basically divide the changes down into control plane and data plane. Basically, every multicast stuping switch is a proxy query that is sending out proxy queries to all of the other ports there periodically. And then there's new timers that are analogous to the query interval and the IGMP and MLD documents for that. And then also talks about how you receive queries. You forward them to adjacent nodes only if they are non-proxy queries. If they are, you don't. And then you will also reply with a report that's containing all the groups in the membership table except the groups where the port the query was received on is the only member port. So that's a little complicated, but basically saying you don't want to tell somebody sending you a report that you also have that group unless somebody else is interested in it. And then we do have a lot of to-dos listed to what happens when you receive reports, transmitting reports, and then also removing groups from the membership table. How do you update the rest of the network to reflect that? On the data plane, we talk about, we divide it into non-routable multicast traffic. So for that, you would only forward a routable multicast traffic to the multicast router port. So if you know FFO2, for example, is a non-routable multicast IPv6
We lost you, Nate.
Sorry?
We can hear you now.
Oh, okay. We also noted the potential for address collisions. And then for routable multicast traffic, specifically for ASM, the router will handle PIM prune messages, excluding those groups back towards the multicast string source. And for SSM, the PIM sends a request to receive the traffic there, so that's already different. So at this point, what we're looking at is comments, questions on what we're discussing here, any sort of comments on what we've laid out so far. Specifically, I would say the use or allocation of the reserve bit there. If we could get confirmation, we're okay heading in that direction. And then we plan to continue refining the document.
All right, we got 1 minute. Any questions for Nate? I think it's just about 2 a.m. for him, so if not, he's going to go to bed. All right, thank you, Nate. Appreciate it.
Thank you.
On the list.
Yeah, right on time.
Yeah. All right, David.
Thank you very much for your time. Today I'm bringing a use case, a problem statement to check if multicast is a solution that we can work together. Um, so distributed consensus is the problem, and it's all about shared state agreement. Currently, applications like file storage, online gaming, and cryptocurrencies try to maintain this shared state. Any change of this state needs consensus among distributed participants. And one key operation that assures these distributed consensus is the majority rule that had been outlined by von Neumann in the 50s. And in this context of distributed consensus systems, there is this new sort of type of permissionless systems that remove the central coordination through an operation that we call the iterative diffusion. So what is this iterative diffusion? Is about maintaining a pool of unicast relations that we call the control plane. And these unicast relations are maintained at the global scale. And on top of that, these pools are randomized and constantly being replenished. So people started to build these to disseminate state changes that are the data plane. And with this operation, the peers cannot really control what they receive because it's only a local validation and they keep disseminating this state. We call this operation an uncoordinated operation. And these are in fact actual common deployments that affect the control plane overhead. So this constant replenishment and randomization that has been designed to cope with churn and unreachability cause control plane overhead in terms of the number of bytes that one needs to establish and maintain these unicast relations. This is done to maintain this data plane. And this data plane keeps being floated in between the pools, and the peers cannot really control when they already received. So we call this data plane overhead, and we measure this in terms of the number of bytes that are being duplicated in the systems. This replenishment and this duplication delay also causes that the agreement gets delayed. So the consensus latency in terms of the time that these systems need to reach this state agreement gets longer. And on top of that, all of these issues, peers can neither judge the dissemination, hence they cannot judge the agreement of the consensus. We call this the consensus finality, and it's just an indicator for determination of the consensus. What is interesting here is that these deployments actually are running in data centers, so hyperscalers, cloud service providers, and ISPs. And the scale of this is not that huge as the real internet. So we think, could multicast come here for better to move from this picture of these uncoordinated operations where peers are establishing relations among them at random and constantly replenished to a more structured way, like this figure, where we call it state replication points, try to orchestrate the peer to SRP communication. So peers do not need to establish this end-to-end relation at global scale, but they only need to maintain a control plane to the SRP. This is an overlay dedicated SRP that maintains these two types of relations, the peer to SRP and the SRP to SRP. We have been comparing this iterative diffusion towards an Stroman architecture that is an overlay. And we outline the benefits that this can have in terms of the number of bytes that can be saved for establishing the relations. So we arrived to this comparison in terms of the control plane can save around 700 times the messages that one required to establish the relations, and 3 times fewer bytes in terms of maintaining this relation once the control plane is established. On top of that, this control plane does not duplicate the state that is being flooded. So it means around 20 megabytes per less traffic per transaction. I forgot to mention that we compared this iterative diffusion from the Ethereum system that is currently deployed at global scale with around 72K peers, so that are deployed in around 10 ISPs. And from there, this comparison is coming from. This control plane establishment and the data plane packet forwarding results in three main stages of dissemination. So it results in a consensus latency being 4 times faster than the one that people realize in iterative diffusion. And furthermore, these SRPs guarantee the majority surplus. So the peers know when the consensus is achieved. I'm happy to take questions in regards of this work. I've been working on the measurement, the modeling, and there are some papers around. And I know I tried to summarize everything, but this is the main idea of the. Happy to take questions.
Yeah, so one question. So all the peers are more or less equal, like all of them may be sending data to all the other peers?
Yes.
Yeah.
That's the main idea of
Yeah.
decentralized participation.
Right.
And do you envision there being any need to make any changes to any flavor of PIM, or do you think you would likely use what we have today and just maybe introduce it to some sort of a distributed consensus system to improve their latency?
Actually, the Strawman already outlines a small feature that probably this multicast enabled pair ISP could do. We call it the counting of peers that could improve on the forwarding of the SRPs. That's a small feature that we envision, but we actually came to here to this group to question that, if that's possible or not, or do you see further solutions or further problems?
Thomas Schmidt from Hamburg. One question. I mean, at least to my knowledge of textbook distributed systems, there has been, I believe in 2017 or so, an improvement of Paxos that's called Raft in NSDI.
Mhm.
That works with multicast, right? So I wonder how this compares.
Yep. So there are kind of two families of these distributed consensus. The Paxos falls into the family of the deterministic ones, and these ones are the permissionless ones. Paxos is built in an entire closed environment, and these guys build among environments, and anyone can join the consensus. In Paxos, you need to select a leader from a non-identified domain, and here the leader is selected randomly from many, from not many, but from 10 ISPs, so to say.
Mankamna Misra, Cisco Systems. So if everyone is talking to every other, so PIM binder may be a better choice than just going PIM. PIM bidirectional, where since everyone is talking to everyone else, so
Yes.
PIM bidirectional will be better choice. Or the variation of PIM. I think Mike was asking if different variation must be used. So I think bidirectional will make more sense for these type of use cases.
Noted. Thank you.
Yeah, and another thing maybe is whether you can expect all of these to have native multicast, or if you need to handle some case where some have native and some need to use an overlay, and how to kind of bridge the gap between overlay and native.
Hi, Dr. Rossen. I'm one of the co-authors. Maybe a few clarifications to the question that were asked. The overlay, going to the question of overlay, the SRPs are overlays. We do envision that the local breakouts would just use native multicast capabilities. That's the advantage of it. And one of the extensions that that David mentioned that could be done, and we're still investigating that if it's actually worth in terms of overhead, is if you do disseminate, you could just simply choose in your local domain to flood. Hence, you send it to the entire group, or you would like to send it to a selected group, which then, of course, has less data plane overhead because you only need to reach, let's say, another 1,000 users in order to reach consensus. Whether or not that's even worth in terms of data plane overhead versus changes to be made in the system, that's something to look in evaluations. But that would require a change because you're not sending it to all, you're sending it to a subgroup, right? But it may just not be worth doing that, right? And you just flood it to whatever it's locally. One of the parts that's really important, which motivated us to look at the multicast part, and that's very possibly a little bit undervalued in the community, is the last point on the slide here that you can see, that multicast really gives you consensus finality. And in order to highlight what that means, in an iterative system, since you're uncoordinated sending to everybody, the only way to judge whether or not you are done disseminating is downloading the result of your consensus. So in a blockchain, that means if you want to see if your transaction made it into the blockchain, you have to download the entire blockchain to check if your entry made it. And that's a huge overhead, given that the blockchain is usually quite large, the ledger, right? In multicast, the operation gives you finality. If you send it, it's being sent and you're done, right? You can do a little bit, and we are evaluating this at the moment as well, a little bit of an overhead. So instead of sending it to the majority, you send it to the majority plus 10% because it's an unreliable service. But the finality judgment is a huge improvement, which is one of the reasons why we're turning to the multicast community to say, maybe you want to do it via multicast, because it allows us to build systems that allow you to realize that your operation is finished without downloading the result, which in crypto is a real issue. Thank you.
Thank you. I need to move on, but there may be a question. Yeah, quick question.
Sandy Nodity, welcome to do some contribution for beer use case draft, because we'd like to move it forward, and if before that you can add the use case in it, it will be very great. Yeah.
Yeah, thanks.
Thanks a lot.
Thank you.
Prasad?
Yes, ma'am. Can you hear me?
Yes.
Okay. So thanks. So I will be presenting experiences with Lisp multicast deployments. This essentially we have the 6831 RFC that is now being moved to standards track. So there is the 6831 BIS document being done at Lisp. Am I audible? Hello. Mike Kustig, am I audible? Can I go ahead?
Yeah, we can hear you, and you have control of the slides.
Okay. Thanks. So yeah, sorry for the interruption. So basically, the 6831 BIS draft is being done at the Lisp working group, and in order to support advancing that to the WGLC and essentially 6831 becoming a full standards track IETF RFC, we had some requests from the Lisp working group to have the Lisp use cases, multicast use cases documented, and so this draft is essentially a support of that. I mean, this is primarily an informational draft, but being done particularly as a separate draft, essentially to highlight the different flavors of multicast deployments we have at Lisp. So that's why we have a separate document and not a section in the 6831 BIS. So with respect to the scope, I think we have from the technical perspective, I think we cover the layer 2 BUM, that is the broadcast, unknown, unicast, and multicast service that can be provided with the multicast underlay. Actually, let me take a step back. I think we should just say that we support deployments of various types of underlays, that is both the unicast and the multicast underlay in the 6831 with both IPv4 and IPv6 kind of combinations. That quite leads to some permutation combinations in the overlay and the underlay. And then with respect to the services, we have the L2 layer 2 BUM, essentially for flooding things like ARP, and layer 2 unknown unicast. You use a multicast underlay to essentially take care of the replication in the multicast underlay. Now, coming to the layer 3, we have, of course, the ASM, SSM, and BIDER, where, the overlay clients can send ASM, SSM, or BIDER, and then these Lisp, these multicast packets get mapped into the Lisp underlay trees that get built, with all the 4 combinations that I mentioned, underlay being IPv4, v6, unicast, multicast, and how you can, essentially have them coexist, because in many real world deployments, we have some coexistence scenarios as well, right? Now, just, in terms of, the types of networks that we have seen, of course, the reason why that is being even highlighted is essentially some of these requirements. For example, the networks built for trade shows or expos are probably slightly different from the networks that are built for hospitals, right? And each of them bring their own a little bit of customization that is needed, and we have a few lessons learned. I'm not going to cover them in the slides, but I think some of them are described in the documents. For example, short-lived flows, announcements like PA systems in the airports, are probably slightly different from compared to long-lived flows. There are some optimizations that we have done, and we'll try to cover them again. Nothing quite different, but just trying to kind of highlight use cases so that people can kind of come to the same page. Okay, so what is not in scope? I think what is not covered is definitely, for example, things like BAER we're not going to cover, or even for that matter L3 unicast, between the sites, right? That is not covered because this is purely restricted to 6831, which is essentially the multicast document. Now, of course, non-Lisp networks are not being covered here. Any kind of MVPN based networking or any other IP multicast is not being covered here. Last but not the least, we're not trying to cover extranet, which is the route leaking part in this document. There is an extranet implementation that we have done. Of course, probably not much deployed as the regular one, but still we have some experience there. But I think we'll try to keep it into a separate document just for the purposes of kind of having the scope defined. Okay, so now, in terms of using PIM over PIM, I think, the reason why, we even did the 6831, I believe, essentially was to reuse the, PIM code base and the PIM, deployments that are very well understood both from the operators and, other people alike. It provides a very convenient method for us to kind of get the multicast service running. Because just the reason why I bring this point specifically is that there is a signal-free RFC, which is, again, also being improved from, rather upgraded from experimental to standards track, which is the native Lisp method of doing things. Essentially having the MSMR participate in the flow, right? And just for the general awareness, the MSMR is essentially the central entity in Lisp which controls the distribution of Lisp overlay reachability information in the unicast world, and there is a way to do that for multicast as well. But that probably did not kind of, I mean, again, the typical engineering approach where you try to do things iteratively, where you try to reuse whatever you have and then try to build on it and then come try to take up the more complicated stuff later. I think that was one of the primary motivations of using the PIM over PIM. I think Stig is here and he can probably correct me if I'm my understanding is not correct. But then the PIM comes up with the cost of essentially PIM hellos and neighborships being cost considered chatty, right? Especially if you have a large number of Lisp sites in the network. I mean, we've seen Lisp sites in the order of few hundreds for sure, right? So then PIM becomes quite chatty, and therefore we had to do some simple optimizations where the PIM the neighborship was kept in a passive mode where the hellos would really not be set, but the PIM neighborship would still come up in a kind of in a pseudo connected state. But then the reachability can always be gotten through Lisp, and we kind of got away with not really having the PIM hellos exchanged. And there is a bit of disadvantage there in terms of heterogeneity being lost, but in a reasonably controlled environment like an enterprise, then where the homogeneity is kind of ensured, is still kind of helps us keep the implementation simple, right? And last but not the least, PIM is also very well understood. So that's one of the helpful factors. I mean, one point I forgot to mention is that a simple optimization was done in the underlay where we only chose to use SSM. And I specifically mentioned this because this takes away a lot of complexity in managing, one layer of RP and one layer of, all the complexity that comes along with synchronizing states between the RPs. So, the reason why we could just simply get away with SSM in the underlay is that any star G or SG is just being forwarded to a particular XTR node, depending upon where the RP or the source is hosted, and that information is anyway being obtained from the Lisp control plane. So we could essentially make that optimization very conveniently and simplify the solution. Right now, a typical campus deployment, again, the reason why I bring up this is, there is a terminology that probably needs some work, how to kind of get it. Probably that is a question for the Lisp working group, but I'm, definitely comments from here are welcome as well. Traditionally the Lisp terminology that is defined by the base Lisp RFCs are essentially every Lisp XTR is considered a Lisp site. Now, in a typical campus, you could have, for example, a multi-site corporate building or multi-site factory floor, right? A multi building factory floor. I'm sorry, right? Essentially, you could have one campus network where there are many Lisp sites. For example, take 2 floors of a building, right? And each floor is just considered as one campus. So I call the word campus here, but it could be even be a floor, right? Building floor, a large building floor, right? Now, what we typically do is for the purposes of administrative convenience, we kind of classify them, and group them and manage them into, in this diagram I refer to as a campus, or some kind of a group of sites, right? And interconnect them with under either the global internet, depending upon if they are very far away connected, or even even another Lisp network where if they are reasonably very closely connected, then you have some L2 connections between them, L2 connectivity between them. Then you have a Lisp, what do you call, a site of sites, right? And kind of interconnect them. So now the question, from the terminology perspective is, what do we really call these campuses? We cannot call them sites because the a site is essentially already defined as very close to an XTR, right? And so there is a little bit of a terminology requirement that is needed here, not just for any specification, because the specification part is all done, but just to document it, right? When you get to document it, there is a little bit of inconvenience on how do you describe it. So that's the one open item that at least I have in the draft. I have shared this with Dino, and I think he has given some comments, and I've been working with him offline. And I try to close the gap with, one word that came up was to have the word domain, being used, right? And then Dino asked me the question, how do you really define a domain? So, we have to figure out a way on how to kind of, carefully define this. But that is just for the purposes of essentially making ourselves clear. But in terms of the actual specification of what needs to be, the procedures that needs to be attached or adapted, I'm sorry, in signaling these flows, setting up or tearing down these flows or maintaining these flows, they're all defined. And quite honestly, this is one RFC where we have a good amount of implementation with a large different deployed code base. In terms of variations, different kinds of networks, and happy to kind of share the experience so that people who are evaluating Lisp, for example, for their networks, right? I think the reason why the sales pitch, I think, as this was referred to in an earlier draft, why do we need this document? Essentially for, I would say, two kinds of audiences, at least 2 kinds of audiences. One, primarily for from the perspective of somebody who is evaluating Lisp for their network, right? What capabilities does Lisp multicast offer me compared to, for example, something like BGP VPN or some other technology? I think somebody can really read through and kind of make sure that what they're looking for can be achieved. And second thing is essentially for other other working groups, essentially BES or people who are kind of interested in doing a cross analysis, a comparative analysis of what are the pros and cons. Of course, everything has got its own advantage or disadvantage, and kind of comparing them, it would really help as well. And last but not the least, even from the objective of making the 6831 BIS to a full standard stack RFC, I think this would be a good collateral to have. So that's all I have from my side. I'll stop here for questions, and any other comments.
Yeah, we need to move on, but one quick question or comment. We published just recently what we call PIM Lite as an RFC 9739, and that discusses how to do PIM without PIM neighbors and how you
Yeah.
still can send joins and so on. And I think it closely matches what is done
Yeah.
with Lisp multicast. So maybe good if you can look at that RFC and see how it fits and maybe incorporate that in your slides somehow.
Yeah, definitely, Stig. Thank you for that comment. Thank you.
Thank you.
Thank you.
Is it called stateless replication with SRv6? Does that sound right?
Something like that.
Something like that. Yeah, okay. Let me give you.
I remember the buzzwords. I don't remember the exact. Yeah. All right.
Hold on, it's not quite there yet. Okay.
All right. Second round here. Okay. So what we would like to propose is to extend the SRv6 architecture with a stateless multicast replication and delivery, right? So same goal as SRv6 unicast, right? So, but of course for us, we don't want to have tree state. We in the network, just stateless replication in the network. Like in the SRv6 architecture as well, also with or without steering. Steering is for traffic engineering. Non-steering is just, best possible delivery. And of course, we want to follow the principles of RFC 8200, which was very painful for SRv6 unicast. So why should we have it any easier? And only change them if it's really necessary, right? So which basically means that in an SRv6 network, the forwarding that customers want to have is through an IPv6 routing extension header, which is also what's done in unicast. So roughly speaking, this document was a quick, starting point into the work. I think we would also follow the way that the work was done for SRv6 unicast. So architecture solution document, which for unicast was done in Spring. And for multicast, I think Spring said something about multicast. What is multicast? Go to PIM. That would be defining and using all this wonderful SID terminology, which I haven't put into this draft yet, right? So I'll probably, rewrite this into more formal language for the next IETF. So that's defining the architecture, the solution, how that would look like. Right now, Spring has really only done very simple things for multicast, which are the tree SID, for example, RFC 9524. So that's really only good for very few, let's call it IPTV trees or so. I'm always calling that multicast PVCs X25, just with SRv6 now. So it's a little bit, so it's certainly not what we need for scaling and dynamic services. And in PIM, we also have a few of these stateful solutions, right? So, but the whole goal is to really have the stateless solution in the same way as also unicast have it. The actual encapsulation, of course, would have to be outsourced to 6-man. Tentatively, multicast routing header. That's exactly where the 8200 rules apply, aligned with the SRv6 architecture. So also trying to reuse and apply as much of the SRv6 extension header functionality and definition as possible. And so the whole relationship, of course, is you first have from the solution working group, in this case, PIM, the solution argument document, and with that, to show the interest of the community, you go to 6-man and let them as the expert review and drive the extension header work. So here is kind of the simple technical proposal outline. So you see down there, typical IPv6 extension header that is pretty much, taken from the SRv6 SRH RFC. There are two main building blocks that are replacing the sequence of IPv6 addresses. The first one is actually the last segment, which is what the receiver will interpret, and that's actually carrying the IPv6 multicast address, or if it's unicast, any new group semantic SID that we want. The second block is then one out of hopefully as few as possible different encodings of the stateless delivery. and then followed by the standard SRH optional type length vector TLV objects, which are not interpreted hop by hop by every router. The first two ones, the MSER and the MRH steering stuff, that is interpreted by every hop. So that is important for the hardware. The TLVs are only important. They're also sometimes done by the hardware, but they're on the exit router, right? And so I've put the details in there. So for example, routing type indicates which routing extension header it is. So there can be up to 256. For unicast, there actually are by now 4 allocated. If you've been following SRv6, you're saying, well, wait a second, it's only 3. Yeah, that's true. SRv6 has only code defined 3, the original SRH and 2 compressed variants. But of course, before SRv6 was done, all the same work was already done by the IoT world, and they actually have the first unicast extension header. So we'll also try to see if or how we can make the IoT world for the multicast happy. If you remember, several years ago, we had these discussions in PIM or BEER in terms of that they were also interested in stateless multicast in the low-end networks. So maybe it ends up in the same way as for unicast, that would be yet another routing type because they have some other metadata. So we'll see for that. So far, I haven't checked it. So then what would be in that subtype block? So this is basically the most simple subtype block, right? So we shouldn't reinvent the world. We should keep everything that is proven to work well. And the BEER architecture 8279 defines a brilliant, simple destination forwarding stateless with a bit string. The only problem that IPv6 networks have is with the hop-by-hop forwarding with the 8296 BEER header, which is exactly what this IPv6 extension header replaces. And that, of course, also makes it a lot more simple. If you see the header below, we only need the architecture elements BSL, SD, SI, the entropy, and the bit string. And then all these other field version, BFR ID, TCS, TTL, DSCP proto that are in the BEER header. That was a little bit of a consortium header, right? So everything was put in there trying to make everybody happy. And we don't need them. These things are in the IPv6 base header that we're adding afterwards. So this is the optimized version, so to speak, for IPv6 networks. And of course, the forwarding hop by hop is by rewriting the IPv6 destination address as in unicast, right? So this forwarding part is all the same as in SRv6 unicast, except of course you're extracting to whom to send the next copy from the bit string, or, and that is the other proposal where I don't have the structure, where instead of a single bit string, we're having a compressed structure representing a delivery tree, and that's a very long story. So there was a lot of work also already done in research. So we had the P4 to Fino implementation for that. We presented most of that work in the BEER working group, just to draw the comparison there. And because we also did BRTE there, which doesn't really work well. And so the steering option has 2 main points, right? One is traffic engineering on top of it, right? It's the steering, the explicit steering, so you can assign resources to that. The second one is that you can actually also make that work much better for larger networks. And so we're having different drafts right now that we need to merge and come up with a common proposed option. And I think one of the important things is trying to figure out if we can come up with a solution that doesn't only work in vendor ASIC, but also in something like Tofino for researchers, because I think one of the big problems we always had is that we need to have more researchers being able to adopt our technologies, verify them independently, and allow extensions from that space. Yeah, so the MSER segment, why do we need an IPv6 address in there, the multicast destination address? Because we want to have a solution like unicast, where I don't need multiple layers to represent that, but it's just end-to-end IPv6 multicast, just without state. So I need to be able to have in the packet, in the same IPv6 header, in the extension part, that address. It's the first one, so that it's at a fixed offset. And that also means that, yeah, you need to look a little bit further down, but it will be possible with a single layer IPv6 header to, again, reintroduce or keep all the ancillary forwarding plane functions that are operating on the source and destination addresses of an IP header, right? So, I was just trying to list the ones that quickly came to mind. There's IPFix for accounting, billing, and other monitoring purposes. There are, of course, a lot of ACLs against source and destinations, really various of architectures based on these address ranges, bandwidth filtering, policing, setting DSCP based on the group address, VRF mapping based on group address range, right? So there were a lot of things done, and by having that address in the header and being that real IPv6 multicast allows to reuse all of these things. So that is also one of the key differences over beer, which puts these things into different layers, right? So beer is at layer 2.5, and then you need to put inside another IPv6 header, which makes all these functionalities now a two-layer, layer violation problem. Yeah, so, and if that destination address isn't a multicast address, then we can come up with new SID semantics, right? We already have two semantics for group addresses, SSM and ASM. So now we even have the full IPv6 address space open and, can use in the same way as SRv6 unicast, the last 64-bit for interesting parameters, programming, and so on. So that's going to be a lot of fun. So summary, right? So this is operationally the most preferable option for SRv6 network operators because it really follows exactly all the SRv6 unicast architecture designs. In the forwarding, it's a single layer network solution for IPv6 with the MRH header, so there is no additional overlay encapsulation to forward IPv6 multicast, and there is no additional per hop tunnel encapsulation to basically make the packets on the wire look like IPv6 as another solution. Support for all the ancillary IP multicast forwarding plane functions or IP header functions because they're all, unicast and multicast. So basically the simple form flat bit string, let's use the beer architecture, that works well, and we don't want to lose the investment in hardware that can do the replication based on the bit string. There's just a slightly different header field, but all the bit string, all the important parts would be in the same way as also in other beer encapsulations. And then the steering solution based on TBD, that's a longer discussion. Yeah, and that's it. Any questions? Overwhelmed. You got 3 minutes.
Yeah, Human, Nokia. Yeah, I was overwhelmed. But just to follow this up, basically what you're saying is that we're gonna do PIM with some kind of a beer header to introduce SRv6 into multicast. Did I get this right?
No, I mean, there is no PIM in this. This is just the forwarding plane, right? So obviously for the overall solution, we're also going to have to say what the control plane is we're having, which is going to be an interesting discussion because most of the SRv6 unicast control plane that we've defined so far is purely for everything where the senders and receivers are routers. So that's all through the IGP. So we'll have to see what we want to do as the control plane for that, right? We can simply follow the IGP stuff, but we can also simply take the thing that we think is the best SRv6 network solution for, signaling the receiver to the sender so that the bit string can be built, right? And we have BGP for that. We have PIM for that, right? So we'll need to ask the SRv6 people, what in SRv6 networks is your preferred option? Is that, I would think, I mean, I for a decade tried to persuade network operators that PIM is great, and then in the meantime, they read everything in BGP. So I would expect that they prefer the BGP option to signal the information. But those control plane aspects, of course, we would do aligned with, what Spring wants.
Okay, so just to be clear, like we tried to do IGP and 3SID, and one of the issues that we start facing is that if you just want to do like a 3SID SRv6 with IGP, multicast is too chatty, right?
Yeah.
So that didn't go too well.
Yeah, there is nothing here in intermediate routers. There is no 3SID. There is no state in any of the intermediate routers because it's just ultimately beer forwarding through the SRv6 extension header.
But then why not just do whatever the heck we are doing in beer right now with?
And that's the long discussion about what do IPv6. So I have appendix slides that is trying to show that, you know, we went through the whole experience once already, right? So customers who wanted to have multicast and the layer 3 VPN service came to us and said, hey, we've got MPLS VPN networks with layer 3 VPN service. We need multicast. Customers are asking for it. We gave them, you know, draft Rosen with IPv4 multicast forwarding, right? And okay, you can deploy it now, right? That was very quick. Is everything working for you? Yeah, everything is working, but we hate it, right? It's not using MPLS forwarding, right? So what difference does it make to you? No, well, it's not our operational model, right? So basically, if you need to use something now, yes, you're going to pick up some, you know, strange beer header that is optimized for MPLS in your IPv6 network. You may have another tunnel encapsulation, so you're ending up with 3 headers, right? And you're grumbly going to accept it. I don't think it's the best way to sell the beer architecture, right? So as soon as the customers are going to have more time, and that's what we're seeing with customers in China, right? They're saying we love the beer idea, but we hate that it's not aligned with our SRv6 network architecture, right? So, you know, up to the point where, you know, you're not going to deliver anything better, and we may give up on the idea of using multicast at all in our network. We're going to wait it out until you come up with a better solution. This is what this extension header is meant to do. It's the operational thing, right? So we had a very strange process which didn't take operational requirements or the, you know, experience we've made in the past with MVPN into account, right? There were so many customers that came back and then said, please do a proper MPLS network solution with an MPLS forwarding plane, right? Instead of going IPv4. Same story, just backward.
Okay, I realize that. I just have one last comment.
Yeah.
I guess we need to understand exactly the problem that we are trying to solve, because right now we have a lot of flavor of stuff and it's becoming very confusing. When you start putting too many flavors, pistachio, chocolate, strawberry, then nobody knows what to deploy and then everything dies anyway. So I'm all like, I think this is great, but let's come up with exactly what we are trying to solve, and then we obviously will
So
go forward.
I think it's very simple, right? It's basically exactly taking the great beer architecture idea and the basic forwarding, giving it the right flavor of encapsulation to get rid of all the state in the network. And then whenever we're running into the networks where I either need traffic engineering, right? Let's not do beer TE because that's, I did the RFC, right? So I know all the pain with it, right? But let's do the more, you know, structured, encoded, compressed trees, right? So, and then if MPLS people come and say, now you did all these cool things for SRv6 networks, right? What are we getting? You know, then we can of course say, well, you can put that stuff, of course, also into a beer header for MPLS networks, right? So
It's got to be really quick, Jeffrey. We got to move on.
Sure, Jeffrey from Juniper. I just want to confirm my understanding here. So in the past, we have talked about 3 options. One is that in the PIM working group, where I believe it was Whitemore proposed to encode a tree or subtree in the MRH. That's one. And then in the beer working group, we talk about 2 things. One is that your RBS stuff, and then then there's a beer v6. So it seems that all these 3 things right now are all put into this document. The beer v6 stuff is basically repackaged into this one as one of the options. Is that correct?
are you fine taking it offline? I mean, I'm happy to also answer on the mailing list, but let's take it offline because it's a longer explanation.
Thank you so much. Luis. Oh, let me give you slide control. Yeah, just push that.
Okay, thank you. Hello, everyone. This is Luis from Telefonica. I will present this document on behalf of my co-authors, Hongji and Shufeng. And the draft is about the proposal of a new YAM data model, well, an extension of the YAM data model for IGMP and MLD proxies in order to support the multipath approach in the proxies. So basically, this document just has a simple recap. Sorry. This is part of a work that has been done initially together with Hitoshi, with the idea of providing the support of multipath in the proxies, basically essentially to have the possibility of activating more than one upstream interface on the proxies. So the framework document, let's call it like that, is the adopted document, the IETF PIM multipath IGMP MLD proxy document, where basically in that document we propose different ways of configuring the upstream interfaces statically, in a statical way or either in an automatic way. So for the automatic configuration, there could be two options, one based on signaling that will require some extensions to the IGMP MLD messages, and the idea would be to leverage on RVC 9279 for that. And this is documented in the draft Contreras PIM multi-if config. And the other option would be the controller-based configuration. So following a kind of SDN-like approach, and for that, trying to, leverage on data models for making that configuration, essentially. And this is the topic of this document. So, yeah, I will go through it. So what we are proposing is, as said, to augment the data model for the proxies and basically incorporating in that data model the necessary attributes that could help us to configure from the SDN controller. So we have proposed the extension, the augmentation now for IGMP. The idea would be to continue with LMLD for sure. And essentially what we do here is to propose the augmentation for those attributes. For instance, the default upstream interface, the interface takeover in case of some failure, what would be the group to be subscribed, in which interface, and so on and so far. So as next steps, we would like to first to collect feedback and interest from the working group. Clearly, we will work on the MLD part in order to make the draft complete. We need to analyze further security considerations. So we depart from the security considerations in the YAN data model, but we need to understand what could be the implications of augmenting that. And then we would like to move forward together with the framework document, the signaling document, and also adding this possibility of configuring through the SDN controller. Whatever comment that we could receive today as well will be incorporated in the document, and the idea is to prepare a new version for next IETF in Madrid. I would like to have comments from the working group, if any. Well, probably we could go for adoption for the framework document. Probably the one for signaling and the one for this as the controller based, let's say, would require more work, at least for this, for sure, because it's version 0.0. But I think for the draft IETF PIM multipath, probably we could go okay. You mean, sorry, I'm a little bit tired. You mean adoption of the working group last call? You mean no?
Adoption of this Yang draft.
The Yang draft. Well, I would wait for having at least the MLD part covered in Madrid, yeah. Sorry, I'm a bit tired yet.
Oh, yeah.
Yeah. Well, it looks useful to have a Yang solution for this, at least to me.
Okay, thank you.
Okay, hold on a second.
Yeah, and this second document is about the proposition of extensions for signaling echo mode, so that either the subscriber or a device on behalf of the subscriber can signal in the echo mode at the time of receiving the contents. So the rationale for this is the following. So the video is basically the major contributor of traffic to the operator's network, and there are even multicast is benefits so much at the time of reducing the traffic on the network. There are yet some aspects that could be improved or could be optimized, let's say. For instance, the fact that in many cases there are the same content is distributed with different resolutions. So basically we are replicating the content, and we are replicating with different bandwidth associated to the resolution that is applied to the video. And also the fact that in many cases as well, the distribution trees are built, let's say, up to the very access with the different flavors of the content. So yeah, even if there are no customers or there are no subscribers demanding it. So the idea for this would be to enable a mechanism that could allow the customer to signal that the subscribers are willing to apply this eco mode consumption. And this could be done either by default, so always assuming that the subscriber will request this eco mode, or even allowing the subscriber to explicitly request this eco mode because of the willingness to do so. So the different benefits that could have this eco mode could be maybe reducing the number of paths of the multicast paths in the network, enabling sleep modes, maybe also the extreme case would be to switching off some ports if they are only devoted to multicast and so on and so far. So what we are doing here is to propose this extension, augmenting the IEMP and MLD messages. And for doing that, we are proposing to leverage on RFC 9279. The idea would be to incorporate this extension, basically indicating the eco mode value, by now very simplistic in this first version, essentially as a Boolean variable. So one would be eco mode set to true, 0 eco mode set to false. And the eco mode will be intended to be supported in both query and report messages. So in such a way that the subscriber can indicate that, or that the network can ask for it. And yeah, I'm basically having in those two messages. The logic behind this eco mode is not yet covered I mean, the logic behind in the sense of what can be done with this eco mode is not covered now in the draft, but we can assume, as said, that could imply optimizations in the network and could be signaled either by the subscriber or even by the device on behalf of the subscriber. For instance, the TV to enter in a sleep mode, or basically this kind of things. No? Or the subscriber just simply being willing to reduce the resolution of the video because he can live or she can live with less resolution content. So next steps would be, okay, it's clear that this is a very basic draft by now. So the idea would be to collect feedback and check if there is interest in the working group in going in this direction. We think that it is interesting because it's somehow the IGMP and MLD messages are somehow a vehicle for the customers to express willingness. So somehow we have direct, we can have the, let's say, collect the direct interest from the customer on this. We would like also to analyze the possibility of more complex coding and logic for the eco mode value. So by now we have the true or false, so I mean Boolean variable, but probably we can, the idea could be to select among different modes, maybe different resolutions, for instance, could be an option. So we will analyze that. We would like also to address the points that could be raised along today and prepare a new version for Madrid as well. So,
Are you taking questions?
Yeah, I thought I turned off my phone.
Okay.
Well, mine is off.
Okay, you're good.
Mankamna from Cisco. So I don't think that even if we want to do some eco known multicast, so multicast protocol may not be the right place. It has to be done in the routing. So if the routing path is being picked using any of these characteristic, multicast will just work on top. So IGMP or PIM extension for these eco mode may not be really needed.
well, in my view, this, as said, this could be just simply a vehicle for taking the willingness of the customer for doing that. I mean, by now we don't have any other vehicle, any other way of collecting the interest from the customer. So that would be this. The implication of this maybe can be activated later on to the routing and so, but we need to understand if the customer or the subscriber is willing to be applied this eco mode for him or her.
Yeah, so I'm far less confident, so I'm more on the asking side. I remember 10, 15 years ago that we wanted to have credentials to allow you to join something. We never got that through, so it's nice to see. I haven't followed all the RFCs that, you know, extensions such as that RFC could be used to do something where we know it needs to get into IGMP. But so yeah, I'm on the edge. So if basically there is, what is it, a lower bit rate, a kind of less energy consuming version of the stream, the application client would tell the server, hey, I want to be, you know, nicely power conserving, and it gets a different group address and, or SSM channel, of course, and joins that, right? So do you have any hard example where that shows it must use the IGMP as opposed to just, you know, joining a different channel or group?
well, I need to think on that.
Yeah.
Probably can come back with more clear examples.
Yeah. And as I said, right, so I think I couldn't find a really good replacement for the access control things, kind of where you have a password or so that allows you to join a channel. So that was pretty good. We kind of could do it now with these extensions, but for the echo, I have no good idea why it must be in the join. So that I think that would be.
Okay, thank you.
Hi, Peter Pshenak, Cisco. So just a quick comment that you are describing some kind of a signaling, but you don't know what you want to do with it.
Well, we have not entered yet into details. I mean, because there could be things that can be done in the network, but also outside the network. For instance,
Well, that's exactly what we would like to understand before we decide whether signaling this makes sense or not, because I think we are going way ahead of ourselves.
Okay, got it. So I will try to provide more details.
Sandy Zhang, ZTE. In fact, I haven't get the logic between the problem statement and the solutions, but seems like this draft will be updated from before next meeting, right?
Sure.
So it's better to add more description about the advantages to use the echo mode, what it will bring for us. Yeah.
Sure.
Thank you.
All your comments are totally fair. So I will try to provide more details and justify better this idea. Thank you.
Thank you.
Thanks a lot.
Thank you.
All right, Bill. You got 15 minutes, and I got to try to find it here. Let's see, what is it called? PIM deterministic.
Yeah, exactly. Hey, PIM working group. It's been 20 years since our C4601 has been published, so I figured I'd come back and say hi. So I'm here to talk about a deterministic ECMP selection in PIM. RC4601 had this really naive statement of you pick the RPF neighbor or the RPF interface. And it was naive because it just assumed there was an answer to that. But if you look at, a modern leaf spine network, there's a lot of ECMP available to you. And so in this example, we have the source over here on the right and two receivers on the two left routers. And the problem comes when leaf 0 picks spine 0 and leaf 1 picks spine 1 and sends their joins in those directions. And then the spines all send their join to leaf 2. This isn't really a problem. Traffic is flowing, but traffic is flowing through both spines. And it doesn't really have to. Because each of these leaf routers make an independent decision about which RPF neighbor they're going to send their join to. So this is just a little bit inefficient. As the scale gets bigger, the inefficiency gets bigger also. This is a tiny little example, so it fits on the slide. So the solution here is for the two leaf routers to do a hash computation on the source group and router ID. And since it includes the router ID from each neighbor, they're going to come to the same decision about which neighbor they're going to use. And so they both come to the decision, we're both going to use spine 1. And so now we have less traffic, we have no traffic flowing through spine 0. Leaf 2 doesn't have to do any replication, it's just sending it towards one spine. And so we have more efficient traffic flow. Wait a minute, you say, RFC 6754 talks about PIM ECMP. Why don't we use that? Well, there's a couple of reasons, but the main reason is because it's designed for an ECMP path between two routers. Router A and router B in the left diagram, they have 4 links between them. And so router B can say, oh, hey, router A, I'm forwarding 90% of traffic over this link, and this other link only is 10% utilized. So why don't you switch your join over to this other link? That's how it works. Is B kind of informs A what kind of join to send it. If you go and look at this diagram on the right, which is a subset of the diagrams on the previous pages, there's no real way for this leaf 2 to tell spine 0 to switch to the spine 1 link. Like that's not how it works. You can't tell one router to start having traffic flow through another router. So that's the first level of this document. Is it describes this hash algorithm, SG router ID, and solves the problem in this kind of network topology. But this kind of network topology, Toiles, do you want to ask now or save it for a little bit? This kind of network topology is, people are growing past this, have long grown past this. So you have leaf spine, super spine, you have multiple replications of this, and they are interconnected by another layer. So this multi-tier fabric, you end up having each of these pods at the bottom level. Well, they can use the algorithm that I've already described here, but you could have a scenario where in pod 1, well, okay, the joins hash to the yellow router, and in pod 2, the joins hash to the green router. They'll be deterministic within the pod, but as soon as you go outside of the pod, you have the same problem at the next layer up. And so in this scenario, you could have that, it gets harder to draw, so I didn't draw it, but you could have the same exact scenario as I had on my second slide, where you have traffic flowing through, in this case, 2 different spines, where 2 different of the top spines, where you could, with the right coordination, just have it flowing through one. And so so the answer here is to have these spines within a pod advertise their color downwards. And so the red spine says, I'm a red spine, the yellow spine says I'm a yellow spine, and then you do the same kind of hashing, except with SG color. And so in pod 1, you hash to SG yellow, and in pod 2, you hash to SG yellow. So every pod is going to hash to the yellow spine for the same SG. And so you get the same mechanism again at the next level. That's most of my technical content. So Troilus, you want to ask your question?
Why don't you go on to show the hash?
The hash is just each router takes, for each of the ECMP next hops possible, it takes either the router ID in the first algorithm or the color in the second algorithm that's advertised by that next hop. It hashes them all and chooses the highest hash or lowest hash or whatever.
So I'm trying to remember all this stuff. This is now more than 10, 15 years back that I last looked at all these things. So I think if you just take, the hash in the same way as, the IPv6 or PIM RFC does it, just, adding the color in there, you're still not having a stable hash, right? So what happens is if a link fails, then you will rehash. It's the modular, the n links, right?
No. You.
That's why I was asking what.
This is okay. So this is stable because instead of hashing and then using that hash to pick a neighbor, we hash every neighbor and we pick the highest value.
Right. So yes.
so it is stable unless the current selected neighbor is the one that goes away.
Right. Right. And I'm trying to remember if we just implemented that or if there's also an RFC for that, because I don't remember. But yeah, so that has been implemented. The color stuff, I think, wasn't implemented, but instead I think the implementations that I'm aware of were using the IP addresses of the next hop. So that obviously wouldn't give you exactly the same results over multiple tier hops, right? So the
Exactly.
color.
The color is introduced in order to handle this scenario,
Yes.
where the decision has to be made all the way at the leaf, but you don't have the information. You're at least one layer away in the network from the thing that you need to hash on, and so that kind of the yellowness gets communicated downwards by a hello option.
Yeah, I think that's. I mean, I do agree that the coloring sounds correct. I need to figure out again what impact this may have if you use it in different topologies. Kind of the polarization issue, which we also looked into, which is in other topologies, right? Like the diamond topology. That's when you're getting polarization based on what hash you're doing. So I'll need to figure out what that is. But obviously, if it's just one configurable, policy, then you may not want to use another policy in other topologies if it doesn't work. And yeah, whether to use signaling or these people have shitloads of configuration, right? I mean, just configuring, I'm just trying to figure out if additional signaling stuff is really that worth it, right? But yeah, the color sounds nice.
Just to give a little bit more about why I published the document, this is something that Arista implemented in its shipping using proprietary hello options. And our customer asked, can we publish it so that we can use other people's routers in these locations in the network. So what that does mean is that the algorithm is different from the PIM, like the hash is different from the PIM hash. I can go into more details, but it's better to hash that out on the list. David?
David Lamparter. Actual clarifying question.
Yeah.
I don't believe I understand why the color is necessary to handle the deep case, because if the last level, like the bottom one in your diagram, is consistent in deciding which middle level it chooses, then that one being consistent in what top level it chooses, doesn't that solve the problem already?
The problem exists in these dots. I said I didn't draw all of the nodes. That was a mistake. I should have drawn all the nodes, and then I could point to the solution, the reason that it's a problem.
So it's not full mesh?
No, the dots mean like all the way on the left it says pod 1, all the way on the right it says pod 120. That implies there's 118 more instances of this in the middle. But the scale is big, and that's why it's hard to draw the actual problem. But the actual problem comes when you have at least 3 of these pods, not 2. This was my mistake in drawing the.
But even with 3 or 4, however many, as long as the inside the box, the bottom layer will be consistent in choosing the first colored layer, right?
But
even without the color.
It's based on in my previous solution, it's based on router ID, right? And so in pod 1 it might choose yellow, and in pod 2 it might choose green, because the router ID is kind of arbitrary, not associated with the color at all.
Thank you. I think I got it.
Yeah, great. Yeah, it's tricky for sure.
Sunny on ZTE, I think this problem is actually true in the large data center. So I think this solution is very important. And I have some question. The first is that in RC 6395, the hello option includes the router ID and the interface ID. So seems like we only use the router ID, right?
Right.
Right. So, okay. And it's interesting to use the hash algorithm. The hash algorithm introduced in the draft seems is very simple, and we'd like to know if the implementation or deployment will show that it's efficiency or practicable. So practicability. Yeah, so we'd like to know if it's really used very good in the actual deployment. So this it's a second question. And then the third question about the color. We think that the color indicates the plane, right? We always use plane in large data center, so I think it's really good. But I'd like to know what value will the color be, because we must use it for hash, right? We must make sure the hash is good and for every selection. So we'd like to know how to set the color's value. Yeah.
So regarding the hash, we have a lot of experience with this hash. You're talking about the hash that's referred to in the document, which is different, very different from the one in the PIM spec. We have a lot of experience with this hash. We use it everywhere in our code base, and we use it in places unrelated to this that are very, very much need of well-distributed hash. And so we have a lot of confidence that this hash algorithm has a good distribution. As to picking the color values, in the current spec, they're 32-bit integers. And because the hash algorithm is quite good, it's very arbitrary. You can pick any non-overlapping values. The hash algorithm will spread them appropriately. So you don't have to worry about how you pick the integers representing the colors of the spines.
Okay. By the way, please ignore my previous email sent in the mailing list.
Yeah, as far as the hash is concerned, so the implementation I know with the stable thingy, right? So where instead of doing the modulo, you're picking the highest one. That's the implementation I know. It's been using the PIM hash. And that's exactly where I told you already on the floor that a couple of years later, some customer came and said, we did large simulations and we're looking at our large service provider core, and it's not really very well splitting on that. So then I was talking with the Scott, and so the recommendation I got for the best hash was Murmur, which has been known to be very good. But yeah, if we're going to pick hash algorithms for this, I guess I would see if we can ask people like him or so to give opinions.
So one of the details about why the spec says use this hash is because half of the reason I published this document is to be interoperable. And so Arista's existing implementation uses this hash. And so it would be easiest to be interoperable if the standard version also used that hash.
Of course.
Okay, with that, we're gonna end.
Okay.
We're out of time. Do you have anything else you want to?
Yeah, no, the question is, you know, is this interesting?
And if you're, are you okay for us to ask the list?
Absolutely.
That question? Okay, that's what, thanks so much.
Thanks.
Yeah, appreciate it. Thanks. Thank you, guys. Oh, is that right?
Distribution is more like an bell curve or something like that worked out. So it's like, think about bell curve as like, let's say you have so 10 options, and maybe the option set which almost never changes. So
I'm trying to remember.
Some of the routers getting almost
That's interesting. I'm trying to remember with Dino working on this gap address. We used a hash method in that 8. I can't remember what the hash was that we used. Beat up. That's what I can't.